So, in general, when we're thinking about coding things up, right? The data science angle that we're taking, the prob stats angle that we're taking, we're thinking about modeling an idea, right? Modeling a phenomenon. And in the past, I would kind of introduce this idea through discrete distributions and have it be sort of an understood underpinning of discrete distributions. And I'm changing that. I actually put together this lecture. I thought this would be a brief lecture that we could do at the beginning of this class for like the first half hour, 45 minutes. I think this is going to take up most of the time today, but I think it's also very important. We want to start thinking about how to model phenomena, right? We want to be able to take some kind of probabilistic process and break it down into its components so that we can start answering questions. And this thing that I'm calling a general analytic approach, this is my, how do I say this? This isn't something you're going to find in a textbook where, this is outlined very, rigorously. What I'm getting at here is that we can come up with a small general set of ways to try to solve almost any problem. And I have 3 different examples of analytic approaches in this lecture. And, there's going to be some live coding, some conceptual questions, and, a series of breakouts as well. But what I'm hoping you'll get from this as we move into random variables and discrete distributions and continuous distributions is that you can look at some phenomenon and you can write code that will help you to answer questions about that phenomenon. Whether or not you have data from the phenomenon, right? Or whether or not you're writing some kind of synthesis of data, right? You have let's say some factory operation, and you have a few numbers out there about the failure of a certain kind of part, like some kind of frequency of failure of a part. And you write some code that kind of details the life cycle of a single part going through this whole process. If you run that a bunch of times, then you've created a model, right? You've created a model for this factory. And you can start trying to answer questions through that model. Now, the validity of those answers is going to be dependent on, say, how closely you are actually modeling the factory. And we do a lot of, hand waving when it comes to some of these things. Like there's the concept of the spherical cow, when a physicist looks at a barn and they're trying to answer the question, well, how many cows can you fit in that barn? Well, let's think about a cow as just being spherical. And the farmer's like, well, there's no such thing as a spherical cow. The physicist is like, that's fine, right? And we're going to just try to pack a bunch of spheres into this barn to give a rough estimate of something. And that's a very valid way of taking a first pass at a problem, right? And in data science, we do this all the time. We look at something and we say, okay, what is the simplest way I can think about trying to answer this? And what kind of success will my solution have? And, what is the threshold of success that I want to achieve? So if I can get this naive solution in place, well, I can start walking toward something that is more precise or more accurate. And we do this all the time. But we need to start somewhere. And most often we look at a phenomenon and we start thinking about how we can synthesize the same data that is in that phenomenon, or we think about how do we get to a point where we can start answering basic questions, right? Like what kind of viewers are watching our cable network, or what kinds of customers are trying to click through on a specific type of ad, right? We need to start from somewhere, and often that's going to be a very naive approach when we start out, and that's good, right? Because that gives us a baseline from which we can build more sophisticated models, whether or not those models exist already out there, and we just apply them and tune them, or whether we invent a new model, which we do from time to time. So the three kind of categories of analytic approach that I'm going to get at here, we've already seen some of this, two of these. Well, really, I think we've seen all three of these in some form. Counting, random sampling, and kind of a closed formula. Okay, so let's break this down. So in general, any one of these, we're going to synthesize some outcomes. Right, we're looking at a stochastic process. We're creating a sample space from that process. So we synthesize some outcomes, right? And we use that to model the phenomenon, or maybe we have some data and we just start looking at that. And then we observe or interpret the values that we see there. And then at that point, we can start answering questions. So we've already done through permutations and combinations, we've done quite a bit of this analysis through counting. And I like to think of this as an exhaustive approach. It gets us what I will be referring to as a theoretical distribution, right? It's something exhaustive. It's got every possibility. And when we're giving a probability, when we're stating the probability of something occurring, we have a type of certainty around that probability because of the frequency at which things occur is detailed in the counting process itself, right? That's what we were seeing with permutations and combinations. Every possible permutation or every possible combination, and then we can ask the question, well, what is the probability of this or this happening? And we can answer that by looking at that subset of outcomes divided by the sample space, the magnitude of the sample space, or the cardinality of the sample space. Now, when I say exhaustive, this is primarily exhaustive for discrete outcomes, and there's a reason why I'm making this distinction, and maybe I can just give a clearer idea of that. If we're trying to model something for discrete outcomes, well, that's fine. Maybe we've got a four-sided die. The outcome from any one of these, if we're rolling it once, this is the exhaustive set of outcomes, right? And the probability of 2 is 1/4, right? So that's easy to see. Now, if we have a number generator that generates values between 1 and 4, and we're asking, well, what's the probability of generating the number 2? Well, depending on the precision of this number generator, right, and we're talking about a continuous outcome. We're not talking about 1, 2, 3, 4. We're talking about 1.0000000000001, however precise we're talking about. If I'm asking the question, well, what is the probability of getting 2, and assuming that this is 2.0, to whatever level of precision, the outcome of getting 2 is very, very low. And so if we're trying to be exhaustive about a continuous outcome, we're going to have a harder time. In fact, it's not possible if the outcome is purely continuous. So in that case, what we end up doing a lot of the time is creating bins. And if we're talking about these outcomes between 1 and 4, we actually will discretize this to some degree, right? Like maybe our bins are, this 1, 2, 3, 4, right? We've got the 1 bin, so values that fall between 0 and 1, between 1 and 2, between 2 and 3, and between 3 and 4. Or maybe we chop that in half and we've got 8 bins or, 16 bins. However we do this, we're going to likely discretize this. That way when we are getting values, if we're going to be exhaustive in our approach, well, we can't truly be exhaustive, but we can be exhaustive in the sense of generating the probability of, say, drawing a value less than, 2.25, right? If this is 2.25, well, the probability that we provide for this is going to be it's going to be pretty good, but it may not be. It's not theoretical. It's still an estimate because we're dealing with some level of precision, and we aren't fully discretizing, right? So I just want to be clear about that. Counting is an exhaustive approach for discrete outcomes. For continuous outcomes, there's still an aspect of estimation in there, where we're trying to approach, right? We're trying to approach the actual value of the distribution. So let's think about a counting example, and maybe I will just copy this. So imagine you created a tabletop game, and this is some kind of D&D style thing, maybe, and the mechanism that you use to battle is first a player rolls a 36-sided die, then they pull a card from a standard deck of cards, and finally the player flips a coin 3 times. So this is a random phenomenon, right? There's a random process here. And we can start to think about how to analyze this. So the first thing we're going to do is synthesize outcomes by counting. I'm actually going to code through this so that we, to explain it as we go, because I want you to see how this type of thing can be constructed. So let me jump over to here. Maybe I'll just move this whole thing down here. Okay. All right. So when in battle, a player first rolls a 36-sided die. So how do we think about that? Well, if we're taking this counting approach, we're going to maybe take a nested loop, right? We might do nested loops here. And I can say, well, our rolls are in the range for a 36-sided die. They're between 1 and 36, right? And I'll just do 16. 1 and 36 plus 1, right? So that represents the rolls. And then next, there's pulling a card from a standard deck of cards. Okay, well, we have 52 possibilities here, right? And it may not be, I could go ahead and do something like cards and start doing something like, well, ace of hearts, and I could start filling this in. That's going to take forever if I try to do that. Why don't I do something a little bit better than that? I'm just going to make the suits, and this is going to be, right, this will be spades, and this will be clubs, and diamonds, and hearts. Okay. And now I can make something else that is the card numbers. So let's do card nums, and we'll do 1. And this is going to take a little bit of time, but not too long, not as much as writing out 52 of these things. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, ace, king, queen, jack. Okay. So I'll just change these to 3, 4, 5, 9 and 10, and then we've got ace, jack, queen, and king. Okay. So to make all of my cards, I can do something like this. I'll make a cards list, and I'm just going to do this in a simple way. So for each suit in the cards, each suit in the suits, and then for each card in the card nums, I'm going to append to our cards an F string that is going to be the card of the suit. And if we look at this, so for card in cards, let's just print each card. And so I believe that'll give us everything we need there. So what is this? Python analytic approach. Okay, yeah. And that's all of our potential cards. And that should be... Let's just make sure. Oh, 56. Are there 56 cards in a deck of cards? I don't play cards. Is it 56? Oh my gosh. Am I doing something duplicate here? Is there no 1 of hearts? There's no 1 of hearts. Okay. Yep. That makes total sense. It's an ace. All right. Well. And that's why I have always lost at cards. All right. Okay, cool. So that's our cards and our die. Now we need to flip a coin 3 times. Okay. So how do we do that? Well, we've already seen essentially how to do this, right? So I'll do coin flips, and I'm just going to collect into there. So for flip 1, in, tails, and heads. Flip 2, flip 3. And then we can append to the coin flips each of those flips in a list. So flip 1, flip 2, and flip 3. Okay. So that should be all of the individual, sort of the constructing phenomena of our random process. So if we want to construct, I'm just going to call this S for now. If we want to construct our sample space S, I can just take for each roll in rolls. Then I can say for each card in cards. And then I can say for each flip in coin flips. And then I can append to each of these, I can append the roll, the card, and the flip. And let's take a look at what this is. So for outcome in S, let's print the outcome. And let's also, after that completes, let's print the length of S to see how many outcomes we have. So it looks like there's 14,976 different ways that this can go, right? And remember, we're modeling some kind of battle in a tabletop game. Okay, so let's... I think there was something in this slide. Oh, it was just that. So the second part, observing, interpreting the values in the list. Well, really, that's just about looking at what happened. And, sometimes this can be fairly involved, sometimes not. I think it's pretty clear what's happening here. And if we think, we're going to think about this in the context of the game itself very shortly. But, we might just be observing how many outcomes there are for 36. So one of the things we can even start asking questions at this point. Well, how many different outcomes can occur with a roll of 36, right? Now, we could do that in a couple different ways. My inclination, honestly, is just to create a quick accumulator to see that if I want, and just traverse this entire thing and say if, list sub 0, if outcome sub 0 is equal to 36, well, let's increment an accumulator. Now, you could do this mathematically too, and that's the thing. Like, we could figure that out. I don't know how to do that offhand. I could probably throw some time into it and figure it out without too much trouble. But then again, I don't really have to, right? I don't really have to because I can leverage Python. I can leverage Python and just traverse this list of outcomes and count how many of these lists have 36 as the dice roll, right? Or the die roll. So this sort of stage, this part 2 of just looking at the outcomes, this is where you start generating questions. Like, what kinds of questions can you ask? And honestly, you can build any phenomenon, right? You can invent any phenomenon in this sense, and you can ask a question and try to answer it, given your sample space. So let's get to part 3 of this, answering questions. And this is going to be a breakout, so put 5 minutes on this. Suppose that the 36-sided die represents the range of an attack, right? So maybe they're squares or hexagons, depending on what level of nerdiness you're trying to get to with this game. To hit an opponent, that opponent must be in range. So, for example, a roll of 29 can potentially hit another player 29 or less spaces away, right? So that 36-sided die roll is going to represent the range of your attack, okay? The card that is drawn represents the amount of damage that the attack will commit, and in order to actually inflict damage, 2 of the 3 coin flips must be heads, okay? So with that, what is the probability of hitting an opponent that is 18 spaces away? So what I'm going to do is paste in the code so far. Let's do this. It's a pretty big block of code. And what I want you to do is write a code snippet that answers this question. What is the probability of hitting an opponent that is 18 spaces away? So obviously you're going to traverse S and collect, and then you're going to do your cardinality of A over cardinality of S to get the probability, right? So yeah, are there any questions about what I'm asking for here? Okay, I'm going to go ahead and put 5 minutes on our timer and do that. Do your best, and I'm going to ask if people need a couple more minutes toward the end of it too. So, if you do, if you feel like you're getting close and time runs out, don't worry. We can add a couple more minutes on it. Give me a thumbs up if you want 2 more minutes on this. All right, so I'm going to code a quick solution here. If you're looking at the slides, the solution in the slides is a little bit wrong, actually, because of my my forgetting that there's no 1 of anything. It's just aces. So let's go ahead, call this Breakout Solution. And the first thing I'm going to do, I'm just going to collect the hits, the potential hits, and the range to the hit. Well, that's 18, so we can hit anything 18 or less. I'm going to say for outcome in S, if outcome sub 0 is greater than or equal to the range to hit, right? And hope that makes sense. So we can only hit on outcomes that are greater than, like the outcome that we get, right? The die roll, if it's 36, well, we hit everything, right? If it's 19, well, then we still hit 18. If it's 18, we still hit 18. But if it's 14, then we don't hit 18. So that's why I'm setting that to that. And I'll just put a second clause here. And outcome sub 2, which is our list, right? That's our nested list. If the count of heads in there, the count of H, is greater than or equal to 2, then that's a hit, right? Okay, so we should be able to append those outcomes like so. And then we can just print the probability here. So I'm going to say round, and I'm going to round this to 3 places, and it's going to be the length of the hits divided by the length of the sample space. So hopefully that's correct. Let's see if we have consensus with what other people got. 0.264? Is that what other people are saying? Oh, good question. That is a really good question here. What did I put in the breakout? Because... oh, you're right. 2 of the 3 coin flips must be heads. Okay. You know what? I just coded that incorrectly. Here. This should be exactly 2. According to the way that I wrote that. I meant to write at least 2, but I think exactly 2. Well, since I wrote exactly 2, let's stick with that. All right, so let's run that and see. 0.198, is that what other people are getting? Yes, it looks like that's what other people are getting. Okay, awesome. So I'll fix that in the notes, because I think I have a couple incorrect things in there in the notes. But this is kind of a way that we can answer questions, right? We've constructed this space, and we can answer all kinds of questions now, right? Like we could consider the what is the probability of doing at least this much damage, on a roll, right? Where we include aspects of the cards, and maybe the way we think about the cards is clubs is 4 hits, and diamonds is 3 hits, and we just add a number of hits, and that number of hits multiplies against the card value, right? So an ace is 1 damage, or a 10 is 10 damage, right? We could think about it like that, and then then we can ask this type of probability that's, say, what is the probability of hitting an opponent that is 6 spaces away, that is within 6 spaces, and doing 40 damage, what is the probability of that? We can answer that question through traversal. We don't need a closed formula to answer it, and that's kind of the one of the things that's powerful about this approach. And when it comes down to it, this is a simple accumulator approach. Like all of this is simple counting and accumulation. That's all this is. And so when Clark and I say things like, you can solve basically every problem with an accumulator, we're not just being flippant by saying that. It's that you actually can. It's maybe not as computationally sound, let's say. It's not as computationally sound as formulating the math for this, but you can do this, and you can do this quickly, right? You can build this within a very small amount of time for almost any kind of random phenomenon that we're considering. So this is wrong. I'll fix this after class. Okay. So that was a counting example, and now we're going to think about a random sampling example. So there are reasons to use random sampling, and I think I demonstrated this a bit yesterday with combinations. We could actually use combinations in a way that was, fairly inexpensive compared to a counting approach. And of course, if we have a closed formula, that's much, much better. But we do have the ability to sample randomly. And then if we keep doing that, we can estimate. The more samples we can take and the more trials of samples we can do, the better we can estimate a population parameter, right? Or estimate a theoretical probability. Now, we can never get the exact theoretical probability because, well, it's an estimate, right? We're randomly sampling, and there's going to be some kind of sample error from trial to trial. That's fine. If we increase our number of samples and if we perform multiple trials of the samples, we do better and better. So let's think about this through this story, this very unlikely story in our current environment. Consider invitations sent for a party. 20 invitations are sent out. Each guest can possibly bring up to 10 guests, with equal probability of, between them not going and them bringing 9 people. Let's say, I think that's how I coded this. No matter what, at least one person, you, will be at the party. So I think this is a good point to start thinking about questions. Is it likely that, because you're only sending out 20 invitations, is it likely that you're going to have a party where nobody shows up? That's the first question, right? And is that plausible? Is that a plausible outcome? Now, I think at this point you might start, thinking about other questions like, well, you need to accommodate how many people? What is the likely number of people that you're going to need to accommodate? Well, this is something that we can do. We can figure this out, and we can make a best guess for the number of people who are going to show up. So let's think about that. We're going to start off by synthesizing our outcomes. And in this case, let's call this random sampling. In this case, we're going to use choice from the random library, and this is one of those functions that you want to have familiarity with. We're going to use it a bunch in the next few days. So I'm going to say from random import choice, and I'm going to write a function here for the number of people attending, right? And this is kind of like this is our guess. This is our guess every time. We know we sent out 20 invitations, right? So why don't I do number of people? At least one person is going to be there. and that's the host, right? So for whatever in range, there's 20 people. Each of those people can potentially bring up to, well, you know, I worded it as 10 guests, and I think I'm going to have to correct the code in my slides a little bit, so I'll just keep with this. So the number of peeps is going to be between the choices of 0 and, well, if it's them and 10 guests, then it's going to be 11 plus 1. Yes. So we can have anywhere between 0 and 11 people arriving based on one invitation being sent. And we don't know how many of those people are going to show up. And we can just return the number of people. Okay. So we have that. And I'm assuming, well, let's just run this, make sure I don't have an error. So the number of attendees, and so 90, 122, 91, 120, 104. That's a pretty big party, right? Now, that's a little bit more like we want to, I think looking at the outcomes here tempers our intuitions, right? So, you know, when I was first writing this, I was thinking, oh, you know, I don't know, maybe it'll be 30 people or something. But it kind of looks like it's going to be more like 100-something people, right? And we can figure out, we can ask all kinds of questions in this regard, but, you know, we can ask, well, what is our expectation for the number of people? And there's a way that we can arrive at that. We can ask all kinds of questions. I think the easiest way to analyze this is through a dictionary. And that's often, yeah, we're going to have a nice little super spreader event over here, and like, you know, it'll be a great time. Now, we can take these values and we can pack them into dictionaries, right? And that's one of the things that we expect you to be able to do. So let's do that. So we're going to observe and interpret the values in the context of, you know, some trial of samples that we take. So, all right. This is fairly straightforward. The first thing we're going to do is instantiate a dictionary. Okay. And I'll just call that outcomes. Some people like doing this. I actually like writing it out, the constructor. So we have an empty dictionary, and then we can sample some number of times. Now, we could do 100. Does 100 seem sufficient? 100 samples? Right, you know, and this is where you have to start thinking about, well, how many samples do you need to start feeling confidence in your data? And I'm going to go ahead and just put 100,000. So I'm going to sample 100,000 times. And for me, that's going to be sufficient. I think we're going to settle with some certainty on the probabilities around certain numbers of guests. And, you know, when we get there, you know, there's all kinds of other questions we could ask, right? Like, how certain are we about a lower number of guests, or how certain are we about a higher number of guests? You know, how much variation is there between trials of samples? We can ask all kinds of questions like that. We're not going to get into that too much here, but we can answer fairly simple questions if we have enough of these samples that we're taking. So I'm going to say outcomes.append. Actually, outcomes. Let's actually sample first. So attending, this is the number of people attending. So the number of attendees, right? Yep. And so that's our count of people who are going to be showing up. So if attending is not in outcomes, then this is the way that I like to do this. I don't usually do an if-else with this. I will initialize the number of people to 0. And then under all cases, I will increment. So this is the equivalent of doing something like this, where we have an if-else, and then this would work in the same way. I do this, it's, you know, either way is completely valid. So at this point, we should be able to take a look at our outcomes, right? We have a dictionary that's packed with the outcomes and of 100,000 samples. So for key value in, now note I need to sort this, otherwise it's going to be completely, you know, it'll just be in the order that I get these outcomes. So I'm going to sort this first, and then I will traverse that dictionary, and we can just print an F string of the keys and the values. So it takes a little while to run, not very long. And we can note what our modal values seem to be, right? We're somewhere in this, somewhere in here, right? And if we really wanted to, we could get the frequency for each of these outcomes, right? Which is 2,447 over 100,000. And then we can multiply each of these by that frequency, and essentially we can figure out an expected number of people who are going to be arriving. And if we run this a few times, you know, we can definitely settle on a number, and I suspect that number is 109, you know. And if we run this again, just take a look if we get something similar. Oh, maybe 110. So maybe right in here. Now, how would we go about gaining more certainty here? You know, sort of discovering what, maybe with more certainty, what our modal count of guests would be. We could take more samples. That's one way, and that's a valid way. The other thing we can do, and I mentioned this a little bit earlier, we can take more trials of samples. So we're doing one trial of 100,000 samples. We could do, say, 100 trials of 100,000 samples and average the results across those. And that's going to kind of constrain in these counts. We just average out these counts, right? And that's going to approach what the theoretical counts of the distribution would be. And, you know, there's a couple different angles we could take on this, right? If we had a closed formula developed for this, well, then, and we got the probabilities out, then we could multiply the probabilities by 100,000, right? And see the theoretical counts. But if we go the other direction, well, we can just run multiple trials of this sampling process and then average the results to approach what the theoretical counts would be. So, from there, we can try to answer a question. So, given a sample of outcomes, provide code to deliver an estimated probability that between 80 and 90 people will attend the party. Round the result to 3 decimal places. So with that, let me give you this code. Let's see. And we're going to take another 5 minutes for this. So again, given a sample of outcomes, provide code to deliver an estimated probability that between 80 and 90 people will attend this party. Round the result to 3 decimal places. So I'll put 5 minutes on the clock. Oh. And go for it. Let me know if you want 2 more minutes on this. Give me a thumbs up if you do. Okay, I'm going to solve this. And let's... Here, I'll comment that out. And actually, let me do this. Okay, so we want to know the probability that between 80 and 90 people are going to attend the party. We're assuming inclusive, right? So we could have 80, we could have 90. Let's think about how to do this. I'm going to do this with a simple accumulator. So just a simple integer accumulator. And I'm going to accumulate into this, but I'm also just, while I'm here, I'm going to get the total number of people. So this I can access with the sum of the values in the outcomes. But, you know, I also already know this. This is 100,000. But I like this approach better because this way I can vary my count of my number of samples, right? I could vary the number of samples. And this would still hold if I'm going to write code in which I want to analyze how many samples I would need in order to kind of settle on a probability without too much variation between trials of samples. Okay, so for attendees in range, I'm going to do it like this, between 80 and 90 people, right? Then I can just accumulate into this 80 to 90 the outcomes sub attendees. So this is first going to look at the count of 80, the number of times our samples yielded 80 attendees, and add that in. Then 81, add that in. Then 82, etc. until we get to 90. All right, so here, I can just, I'm going to round this to 3 places. Oops, let me do this. There we go. This is going to be 80 to 90 divided by the total. And I think that should work. So I'm getting 0.071. Is that... Oh, yeah, that sounds about right, right? So I'm seeing 0.073 up here, 0.073. If I run this again, I'm likely going to get a different value. I get 0.073. Now it kind of is settling right around 0.073, right? 0.071, 0.074, and I've got 0.073 a couple times. I don't know this, but my suspicion is that if we ran this many, many trials, that we would see something that looks like 0.073, be our estimate of the theoretical probability of getting a value between 80 and 90 people. Okay. So let's take a break here. Let's take 6 minutes, and I will see y'all back here then. And oh, is there a question? Oh, you can't see exactly what... Yeah, why don't I talk to this right before we take a break? So, what do our keys and our values represent? Values are the amount of people that come. No. Okay, so let's look at this in terms of our output. So let's do that. Yeah, and I think this is often a confusing thing about sampling. We are modeling this phenomenon, but of course we only have one party, right? So we're modeling this party as if there are 100,000 parties where we, sent out 10 invitations every time. And so we do this one time, and then we get 61, and then we increment the number of times we got 61 people to 1, and then we do this again, and we get 116, and then we increment 116 to 1. We do this, after we do this 100,000 times, we filled in the possibilities of getting anywhere from 49 people attending to 178 people attending. And notice we have these sample gaps, right? We never see 173. We don't see 176 here. We don't see, well, it's pretty consistent going down after that. So, yeah, if I run this again, it's going to be different again. And now we get 170, 171, and 172. So values are the number of times the key happened, and keys are the number of people. That's exactly correct. That's exactly correct. Yeah. Awesome. Okay, let's take 6 minutes, and I'll see you all back here momentarily. Okay, so we've talked about the counting approach, and we've talked about a sampling approach. So those are going to be if you have kind of an unknown phenomenon, then those are likely what you're going to use, right? You're going to use either a counting approach or a sampling approach. Now, there are a lot of cases though where you have some kind of closed formula, and we can think about a lot of different formulas. Really, we can. Maybe the sigmoid function, which is used to, also called the logistic function, which is the classic underpinning function for neural networks, right? That's the type of function where we would just code the function itself, just a simple mathematical function, and potentially, make an array of those in order to build a neural net. That's something that we could do. Yesterday, I implemented the heaps algorithm, right? And I implemented a combinations algorithm. Now, I wouldn't call those closed functions, but those are sort of closed solutions. They're not very exploratory, really. They're not sampling. It's something that pre-exists. In fact, I could call out to, a pre-existing library that has some optimized form of the heaps algorithm in order to generate permutations. Now, I'm going to use a very simple example here that involves volume of a sphere. So our problem statement is, consider a collection of spherical containers used to hold super gumballs of radius 1 inch. Okay, so there's like this consistent size of gumball that we're thinking of putting into different sizes of spherical containers. The containers range from 4 inches in radius up to 100 inches in radius, and we want to consider the rough count of gumballs per sphere based on the radius of that sphere. So the first thing we can do here, this first step, we're going to synthesize outcomes, and we're going to model this phenomenon. Now, why don't we do that? That's fairly easy to do here because we have this closed formula, and that's, I think, generally what you see with these closed formula solutions. You are just calling out to something that you wrote or exists already somewhere, right? We could do this with factorial. We could do this with any number of things. So I'm going to need pi for this, and I'm going to import that from math. Import pi. And this is just the simple spherical volume. So that's 4/3 pi r cubed. So let's do that. Spherical volume. And we pass in the radius. And we can just return 4/3 times pi times r cubed. So we can look at the spherical volume. Spherical of, let's say, 10 inches. I think I'm using inches here. And I'm still running some code up here. Let me comment that out. Yeah, that works. Outcomes is not defined. Try that again. Okay, so that's 4,188 inches cubed. Cool. So that's easy. Now, when we're thinking about how to observe outcomes here, this is, again, something where we, if we're observing this, again, we're just going to pack these into a dictionary, and that's going to be easy enough to do. In fact, it's going to be somewhat easier than the last one, because we don't have to qualify for membership, we're going to be inputting a radius and getting a result. So the key will be the radius, and the volume will be the value. So remember, though, we are relating the number of gumballs that can fit in a sphere to the radius of the sphere. And here's where things are going to get a little hand-wavy. And I'm going to ask you why that might be a little hand-wavy in just a second, and see if anybody has a quick thought on that. So I'm making a dictionary, and I'm going to say for radius in range, and we'll go from 4 up to 100. That was the range that we were considering. And the dictionary, where the key is the radius, is going to have as a value not just the spherical volume, right? Spherical volume of R. I'm going to divide this by the spherical volume of a single gumball, okay? Right? Because we're thinking about the number of gumballs per sphere. So I'm just going to do that. And we're thinking of the number of gumballs that can fit in a sphere as being a discrete value. We're not intending on putting partial gumballs in these. So I'm just going to cast that to an int. And I can return the dictionary there and say for R be in gumball capacity dot items. Notice I don't need to sort this because this packed into the dictionary starting at 4, and there is a even though we don't guarantee order in dictionaries, the newer versions of Python do sort of guarantee that, so we should expect to see these keys in order. And I can just print an f string R and V. Function object has no attribute items due to that. Okay. So let's take a look at this, and we can think about how the capacity of these the capacity of these spheres grows as the radius increases, right? So we can see that this is not linear growth, right? Like this is growing increasingly with the volume. And the question that I mean to ask here, and this is a bit of a side question, what might be wrong with our estimations of the number of gumballs that were fitting into these spheres? Any thoughts on that? What might be a little bit naive that we're doing here? Yeah, we're missing lost volume space between the balls. Yeah, definitely. We're doing something naive here, and so the actual math that we need to do here to make a better version of this this model, or this description of the phenomenon, what we'd actually have to do here is quite a bit more complex. But we're going to assume this to be good enough, right? That's what we're going for here. We're going for something that's our first pass, and we're going to assume this is reasonably okay. And just to drive that point home, I can just do a very quick drawing. Even if we're thinking about this in terms of circles, right? We need to consider, maybe in a more sophisticated model, we need to consider those spaces, those air gaps that we can't fill in. Cool, thanks. So, this is kind of just getting at a point that I'm gonna try to make later in our last couple of days of class, that we don't have perfect models, and we are usually trying to make a model. We're trying to describe some phenomenon in a way that meets a threshold for us, right? We're like, well, we need to make this good enough to solve our problem. We don't necessarily need to take it much further than that. It doesn't have to be perfect in really any case, in very few cases. Sometimes we need more precision, or sometimes we need more accuracy, or something. But in a lot of cases, we can take a somewhat higher level, somewhat more abstract approach and get something that's good enough. So we're going to assume that this is good enough, and I'm going to paste this in. And your breakout on this is you're going to write a function called getSphere. And that's going to take in a number of gumballs, right? Like, say you get, you have this varying, for whatever reason, some varying inventory. Like maybe they send you a different number of gumballs every couple weeks, and you need to select the correct sphere to best accommodate that inventory, because you don't want to have more than one sphere, right? You just want to have one sphere that you select. And if you overfill it, well, that kind of sucks. You don't want to do that. So you're going to return the radius of the sphere that's necessary to accommodate that inventory. That's the goal of this function. So I'll go ahead and put 5 minutes on our timer. And yeah, do your best on it. Okay, so let's go through a solution of this. And, you know, this isn't... our prior questions were probability questions, but you're not always answering a probability question, right? You're looking, you're doing some kind of analysis, and that might be, well, what is the probability of this happening, or something like that. But in this case, we're just asking and answering, we're answering a very basic question, right? That isn't probabilistic at all. We could make probabilistic questions for this, but in this case, we're not. So get sphere. And I don't know, gumball inventory, I think is what I called this before. So I'm going to get that dictionary of the gumball capacity, and I'm going to traverse it, so kv and d.items. And if the value is greater than the gumball inventory, right, where the value is essentially the volume, right? If this is better, better than, this is, the value is how many gumballs we think we can hold. If that's greater than the inventory we're seeing, then we can just return k. And I'm just going to throw this in here. What if we have too many, right? Then we're going to return none. And maybe I'll just say no appropriate sphere available. This is a good case for having an error return, you know, that's, or throwing an error, which is something Clark's going to cover in another class if he, I'm assuming he hasn't covered it yet, but handling errors. We don't need you to know how to handle errors at this point, so this message is just, you know, a simple way to do that. And yeah, let's see for 10,000 of these, and maybe I'll still print these out so we can just take a look. Okay, so it looks like a radius of 22 inches, and I'll just scroll up and see if that should accommodate 10,000. It looks like it does, 10,648, so I think we're doing well with that radius of 22. Okay. So I think that's all I have here for the analytic approach notes. Let's. I thought we wouldn't have quite this much time, so that's awesome. We can get started on random variables, and we might even get into Bernoulli, the basis for Bernoulli and binomial. So I'm going to. I think I'm going to switch almost solely to pen and paper for a little while. And maybe we'll jump back to coding at some point. Okay, so we have this concept of a random variable. And we've been working with random variables without really calling them that. And I just sort of want to formally, you know, consider what these are. So the way that I'm going to describe a random variable is as the outcome of, like a defined outcome of an experiment. And maybe we can start this off with something very basic. And I'll say the random variable x represents the count of heads in 4 flips of a fair coin. Okay. So we can ask a question about the random variable x. We can ask the question, what is the probability that x is 3. So think about that. What is the probability that x is 3? How can we approach answering that question? Any thoughts? How we can approach answering that? It might be easier to answer this question. What is the probability that x is 0? Right? This is going to be the outcome tails, 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 tails. So what is the probability of tails, 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 tails? Well, there's only one outcome of 4 coin flips where we get 4 tails in a row. So that's kind of cool. Like that's a good way of thinking about that. So this is actually going to be one outcome over something. Yeah, and that's this is actually going to be 1 over 2 to the 4th. And we can also think about this as 1 half times 1 half times 1 half times 1 half, right? So we've got 4 flips in a row. Each of these have a 0.5 probability, so it's 1 half to the 4th power in this case. This is kind of nice. This is kind of convenient because we can see that there's only one outcome out of 2 to the 4 outcomes, right? This one's a little trickier, and it's trickier because we're talking about 3 heads, and those heads can be arranged, let's say, heads, 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 tails, heads, heads, tails, heads, heads, tails, heads, heads, tails, heads, heads, heads. And I think that's it, right? So we've got 4 outcomes here out of 2 to the 4 outcomes. So this is kind of, when we're thinking about how to describe a random variable, right? The outcome of the random variable here is defined to be the sum of the number of heads, the sum of the occurrences of heads. The random variable isn't described as the individual outcomes of 4 coin flips. It's actually the sum of heads in those coin flips, right? So when we're saying x is 3, we're asking how many times, if we look at the underlying process, how many times do we get 3 heads out of 4 coin flips? But at the end of the day, we're talking about the sum of heads as the result in this random variable. So that's one example of a random variable problem. We can ask other kinds of questions, defined by in terms of random variables. So let's say we have a random variable y, and y represents. How about let's do just another simple sum one. The sum of values in a randomly generated how about a randomly generated list of trinary let's do 3 of length 3. And then we can ask the question, what is the probability that y equals 1? So now we need to think about this again in terms of, we can think about it in terms of the sample space, but really think about what y represents. Y represents the sum of that trinary. Y does not represent the underlying process, right? The underlying process in trinary is going to be something like this. We could count it out: 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 1, 0, 0, 1, 1, 0, 1, 2, and so on. And we can think about how to answer this question in part in terms of, well, how many outcomes are there for y, right? We can think about that. And the number of outcomes for y, what is the number of outcomes for y here? Yeah, we're thinking 3 to the third power, right? Because we've got a base 3 system, and then we've got 3 digits of that, or 3 numbers in that. And so if we're talking about the outcomes where y could equal 1, well, that could be 0, 0, 1, 0, 1, 0, or 1, 0, 0. That's 3 over 3 to the third power, or 3 out of 27, or 1 over 9, right? So the probability y equals 1 is 1 over 9. Let's think about another random variable. So the random variable z, how about that? Random variable z represents the number of planes that land at the airport between, how about 1 and 3 p.m. So we don't have we need some prior data here, right, to be able to describe z. But we can still ask this question and explore, how to get to an answer. We can ask the question, what is the probability that z is 67, or is less than or equal to 67? So, we probably would have our averages for given work days in some season. Or maybe we would have averages. We would have to think about this a little differently, because maybe it's, if we're saying between 1 and 3, well, there's different travel rates on different days, right? So maybe we need to really hone in what we mean by z. Maybe z doesn't just represent the number of airplanes that land between 1 and 3. Maybe z represents something like on a Saturday, or on a given Saturday in July, right? And maybe we need years of data in order to have an estimate, to have some estimate of what we would expect this number to be given, our current position in time, and given the economy, given all these things. So we would have some projection of probabilities. But I want you to notice that we can define a random variable to be to represent the outcome of an experiment, of an observation of a phenomenon, however we want to think about that. In these cases, I've been using discrete random variables, right? And they're discrete because we can count the outcomes, right? We don't have a partial plane landing. We have a plane, or we have 2 planes, or 3 planes, or 170 planes. We don't have 170.1 planes, hopefully, right? So this is kind of the core idea around a random variable. It gives us a convenience in representation. And we can take the same phenomenon and define different random variables for that phenomenon. So let's go back to an idea of binary. Instead of using coin flips, I'm just going to call it binary now. And let's say we have, heads represented by 1 and tails represented by 0. And we're talking about 4 coin flips, or 4-bit binary is what we would call that. But let's still kind of think about it like coin flips. So 4 coin flips. We have a random variable, how about a random variable A, and A represents the occurrence of 2 heads in a row. Okay. And we have another one, B, that represents the sum of ones. Okay. So notice we've got 2 very different ideas here. We have, if we have this binary outcome 0, 1, 0, actually, let's do this. If we're thinking about this binary right here, 0, 1, 1, 0, the result of the random variable A is going to be, we could say it's true. Now, if we have 0, 1, 0, 0, then the result of A is going to be false. And we don't have any other results for A. So A just represents whether or not there are 2 H's, 2 heads in a row. Now B, the outcome for B here for 0, 1, 1, 0 is 2. Oops. And the outcome for 0, 1, 0, 0 is 1. So notice A and B are both dealing with the same phenomenon, but we've defined them differently. And this is the convenience of definition that we're dealing with here. This is why we use random variables. And the way that we're going to see these kinds of problems is, random variable X represents blah, blah, blah. What is the probability that X equals something, or X is greater than something? So that's a little bit about random variables. We're going to continue to see random variables. And, if you think about it, we've been seeing random variables for a bit of time here. I just haven't been calling them that. Okay, so let's start thinking about our discrete distributions. We've been doing stuff with discrete distributions, and I haven't been saying that, but we've been doing that. So what do I mean by discrete distributions? Well, it has the word discrete in it. There's probably some phenomenon that has countable outcomes, and that's exactly what this is. Now, what separates a discrete distribution from a continuous distribution? In some fundamental way, not that much. In a theoretical sense, not that much. But when we're programming, quite a bit. Or when we're looking at this from a more classical stats perspective, quite a bit. And so the way that I'm going to kind of distinguish these two, discrete from continuous distributions, at least for the moment, is through a very simple graphic. So the sort of cardinal, the cardinal continuous distribution that we're always referring to is going to be the normal distribution. Looks something like that. And the main discrete distribution that we tend to refer things back to is called the binomial distribution, and it looks something like this. And one thing to notice is that this has a bell-shapedness about it, a kind of normalcy about it. And if we were to discretize the normal distribution in some way, it would look a lot like a discrete, it would look a lot like the binomial distribution. So just as a reference point in terms of distributions themselves, I would think of, just a flagship for each of these, right? So the flagship for the discrete distributions is going to be binomial. And the flagship for continuous distributions is going to be the normal distribution. We're going to spend the next 3 classes talking discrete distributions, and then we're going to spend 1 class on continuous distributions. This is a little bit different from most courses of study when it comes to the distributions. Most courses of study will take kind of a lot of time with specifically the normal distribution. Most stats classes will spend a massive amount of time on the normal distribution, and there are reasons for that. In terms of experimental design, in terms of confidence intervals, and these things that you're going to learn in the DSI, most stats classes will focus in on continuous distributions because, well, in part because if you're taking a stats class, the part of the intent of that is so that you can go read research and read the outcomes in research. And when somebody publishes something, they say, well, here are the results within 95% confidence or 99.5% confidence or something like that. And that those confidence intervals are defined through an idea of the normal distribution. So that's a great reason to teach the normal distribution pretty extensively. We teach the discrete. We teach discrete distributions in part because we want to students who are coming into the DSI are going to learn a more data science-y form of experimental design and a different way of qualifying uncertainty or confidence in the outcomes of an experiment. And so that's going to look a little different from some of the other sciences. And so we want to kind of set aside, not fully set aside the normal distribution. We will dig into the normal distribution, but from a very procedural standpoint, we're going to implement something that will get the probability of a normally distributed event occurring. We're going to write code that will do that. But we're going to spend kind of a lot more time on discrete distributions because it's easy to see the underlying phenomena that from which we can derive the discrete distributions. So I'm going to list the discrete distributions that we're interested in this course. And we're going to start it off, everything we're going to root back to something called a Bernoulli trial. I think throughout our materials, we actually call this a Bernoulli distribution. It's kind of a weird one, to call, in my opinion, to call it a distribution. Not wrong to call it that, but a little weird to call it that because there are only 2 outcomes, and there is a fixed probability around those outcomes. So we have about 10 minutes. Okay, cool. Yeah, so you know what? Let's dig into this just a little bit. A Bernoulli trial has a binary outcome, okay? It can be one of 2 outcomes, and we'll often, throughout this course at least, we're going to refer to the outcomes of a Bernoulli trial in terms of binary, okay? So I'm going to call this a binary outcome that includes 2 things, 0 or 1. We can think about this as failure and success. So notice that when I say failure, I'm referring to 0, but we could swap those. We could say that 0 is a success and 1 is a failure. It really depends on how we want to think about the problem. The other thing to consider here is that there is a probability of success. And I'm going to call this a parameter. There's a parameter to the Bernoulli distribution that we call P, and that is the probability of success. Okay? So if we think about a Bernoulli trial as being this fundamental building block, then we can take this further and think about, well, what if we have a series of Bernoulli trials? If we have a series of Bernoulli trials with a fixed probability P across all trials, like let's say we have 4 coin flips, right? There's a 50-50 chance for each trial, unless we swap in some other coin that's unfair, but then, you know, we're dealing with some other distribution that we don't have clearly defined. If we have a series of Bernoulli trials where we know the number of trials and we have a fixed probability P, we call this binomial. And I tend to refer to this as a distribution. Feel free to call Bernoulli a distribution. It's not a distribution. I just think of it as a single trial, so I have a harder time thinking about it that way. So with the binomial distribution, we have essentially a binary word, what I'm going to call a binary word outcome. And all I mean by binary word, we don't call binary numbers usually, although maybe I'll just do that because it's easy to think about that. But if we have multiple binary bits, right, ones or zeros, so I could say 0, 1, 0, 0, 1, 0, 1. If we think about this, this is something we might call a binary word. And the binomial distribution, the way we think about this, is the number of successes. The number of successes in n trials with probability P per trial. So in this binary right here, and maybe I'll just do this. So what was that? 0, 1, 0, 0, 1, 0, 1, maybe? Something like that. This is a failure. This is a success. Failure, failure, success, failure, success, right? And if we're thinking about this in terms of binomial, right, then the outcome here is 3 successes. This isn't the only way to get 3 successes. We could get 1, 1, 1, 0, 0, 0, 0, 0. That would also be 3 successes. We could get 1, 1, 0, 1, 0, 0, 0, 0. That would also be 3 successes. So notice, implicitly here, we have a combinations problem. And we're going to see that come back around. Now, there are 2 other discrete distributions we're going to consider. The next one I like to think about is called Poisson. And Poisson seems like it's some kind of divergence away from binomial. It turns out that it is directly related to and derived from binomial, but let's just think about what this is. If we know the average number of events in some length of time, let's say, in some length of time, and we hold a number of things constant, like the events are independent of each other and they're identically distributed to each other, right? there's a consistent rate of the events. There's no effective seasonality or time of day or anything like that. If we can make those constraints, then we can estimate the probability. We can get a probability of k events occurring in that time or another time in some span of time. I'm putting this in terms of time because we are often thinking about Poisson in terms of time, but this actually applies to area as well, or volume, or to the occurrence of a word across a number of pages. The Poisson distribution can be used in a lot of different domains. Now, I'll try to make a basis for how Poisson is comes from binomial, but for now, let's think about this as the distribution we use to estimate the amount of occurrences in some span of time. And then finally, the last one that we're going to talk about, I think we'll do Bernoulli and binomial for 1 or 2 days, maybe 1.5 days. Then we'll do Poisson, then we'll do geometric. Geometric is the number of failures. Let's think about this as the representing the number of failures in Bernoulli trials, right? Up to the first success. So this is going to give us, again, this is going to give us binary. And the binary is going to look a bit different. In this case, instead of having 0, 1, 0, 1, 1, 0, or something like that, we can only have zeros. We can't have any zeros or ones after our initial 1, right? If we're thinking about this in terms of failure and success. So this could be a geometric outcome, or this could be a geometric outcome, or this could be a geometric outcome. Notice that each of these zeros representing failures, this is failures up until some success. And this is somewhat of a simpler distribution. Yeah, we can think about order as being important in geometric. In fact, geometric is sort of about order. It's, in a very basic way, it's like, okay, well, failure, 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 success, or failure, success, or success, right? And so when we're thinking about K, what I'm going to call K is going to represent the number of failures up to the first success, or up to and including the first success, depending on how we want to think about it. You're going to see K, a different definition of K for geometric, for binomial, and for Poisson. Very different ideas of K for each of those. But K here is going to represent the number of failures in Bernoulli trials up to the first success. So, if you want to think of a specific problem with this, well, how many times do you have to flip a coin before you get a heads? And you can sit there and record this, right? You could flip a coin and keep flipping it, and maybe you flip it 3 times, and then you get a heads on the 4th time. So you write down 3. And then you get a heads on the 1st time. So you write down 0, right? You get a heads on your 2nd flip, so you write down 1. And I think if you did this, 30 times or something like that, and you average this all out, you would see that the probability of heads is going to equal 0.5, right? I mean, we would assume this anyway, given that it's a fair coin, but what if we didn't know if it was a fair coin? We could use geometric to kind of look at the outcomes. We just keep flipping the coin, and then we could actually discern the probability of any given outcome. But then with geometric, the kind of question we can answer is, what is the probability that you get 5 tails before you get your first heads. And turns out that's a very low probability, right? It actually is. And we could tabulate that in, or we could do the arithmetic for that in a number of different ways. We could actually count out the sample space if we wanted to. That is something we could do. Awesome. So that's just a little bit of a preview for the next 3 lectures, which are going to cover, tomorrow we'll do Bernoulli binomial, then we'll do Poisson, then we'll do geometric. I'm going to be using these analytic approaches for all of those. For binomial, I'm going to use all 3 of the ones that we described, the counting, sampling, and closed formula. For Poisson, I'm probably just going to use the closed formula, unless... but sampling for Poisson is actually really cool, so I'm thinking about it, but it might just be too much. We might not be able to fit that in. And then geometric, we'll do both we'll do closed formula and sampling for that one. But yeah, that's it for today. Stay on if you have any questions. I'll stay on for, again, 10 or 15 minutes. And otherwise, have a great night, and I will see you all tomorrow. Actually, I might swap classes with Clark tomorrow, so I might not be on tomorrow, but probably will be. So if I'm not, don't be surprised. But if I am, we're going to be starting in on Bernoulli and binomial.